So thank you very much for hosting me online. Even I will be more than happy to come in person and see you all. Oh, actually, I can because 3 days ago I got my second vaccine from Pfizer. So in 4 days I'm immune. So maybe in a few weeks I'll be able to come and see you guys in person. So thank you first of all for the organizers. I do want to say that I have my colleague here with me. His name is Jos. He's a part of our part of our sister company, Samsung Netherlands. Obviously, he speaks Dutch, so if you have any questions and you want to ask it in Dutch, or if you're looking for some answers in Dutch, feel free. He speaks very well Dutch and knows very well the solution as well.
I do. Good afternoon. Goedemiddag, mensen. Yeah, I will monitor the chat box and try to interrupt you when questions are coming. So
wonderful. Yeah. So thank you for your support, Jos, and thank you for organizers and to all the participants. And yeah, so what I'm here is to talk about a bit about AI approaches, specifically for the process industry, and why the process industry is so unique and needs something which is very, very specific to its own needs. So before I start and go into the details, a bit about ourselves. So today I'll present to you what our solution or the area around what we do is, we call it SamGuard, which is a human-enhanced machine learning software. I'm very biased, so I will say that I really believe that we have one of the best solutions out there. It's not because we were a small startup company in Israel until Samsung AG acquired us. It's maybe part of it, but because mainly we have quite good experience in the area. Our company was established in 2011. The product was out in 2015. And you probably know that not a lot of people talked about AI in 2015, and definitely none of people talked about predictive maintenance back then. I think that it just started in 2017, so we have quite a lot of experience coming within solutions of what you guys as customers needs. What pain can we solve? And what I'm very proud of is that our machine learning is not here to replace anyone. It's doing the opposite. Our machine learning is here to make engineers better, smarter, take faster, and more data-driven decisions, which I think it's amazing because we make technology makes us better instead of replacing us. A bit about us and Samsung. So I like to call it, it's a very nice combination. It's an amazing hybrid. When a small startup innovating company, we're acquired by the big, huge manufacturing companies such as Samsung, which I refers to where innovation meets tradition. And this combination is awesome. So you all know Samsung, which has more than 113 years experience in the industry, thousands of employees, subsidiaries worldwide. We specifically were announced as Tech Pioneer in World Economic Forum in 2018, and we have a patent on our AI. And most of our development based in Israel is still based in Israel. We are focusing only on process industries, so from chemical, petrochemicals, refineries, oil and gas, pulp and paper, cement, and so on and so forth. We are now starting to enter pharmaceuticals and also mining. And we are spread globally, so we have projects in North and South America, Europe, Asia, East. We have very nice partners under our hand, but enough about us. Let's see what's the issues and what are the solutions. So what we're seeing is there's very good and very nice buzzwords in the industry, and the biggest one today is operational excellence. And how can you get there? Because everybody wants to be there. And what we do is helping our AI is helping our customers basically reach to operational excellence by first of all lowering maintenance costs, able to lowering labor costs, not by reducing people, but instead of keep running fire after fire or chasing fires, do it in a more manner and a more stable and more relaxed way, and by that to increase availability. So what we see is AIs can help with basically early failure detection, both on static and rotating equipment parts. Assist with process deviations, which is kind of combining each other, but there's very rare cases of only process deviations. Operator mistakes, which we see a lot. I know somebody changed the set point. Why? Nobody knows. Maybe it was young, it was late. They did not open a valve, and then there was ammonia was trapped in the pipes, and the pressures keep coming up. Nobody wants an explosion of ammonia in any plant or any place around the world. And of course, which is something which is everybody is trying to talk about, is try to reduce as much as possible unexpected issues and unexpected shutdown, because the cost here is not about how much it costs us to fix, and the cost of the equipment is the cost of production. And this is what we see is this is how you can actually reach operational excellence and with increasing the availability. And if we let's talk about challenges, because that's why you brought me here. So what we see is that a problem can happen anywhere. It can come from a valve, come from a pump, from a heat exchanger, from compressor, from turbine, from a small mechanical valve. And this is one issue. There's a lot of equipment, a lot of manufacturing, different data on each equipment, even if it's the same manufacturer. But there's a lot of data, which is the positive side. What we see is that it's very rare for me to see a company, especially in Europe or North or in Americans, that don't have data, so there's a lot of data available. Now, where's the challenge? The challenge is that there are very few identical historical problems. Now, I'm sure that each and every one of you in the room will go back to your ERP systems or any system that you are capturing your past failures or issues. You will see that every failure is different. So even, and this is very rare example, even if a pump or a compressor or heat exchanger or reactor or any valve will fail 3 times in the same year, which is super rare because the equipments are very stable and they have good reliability on them. But even if the pump failed 3 times in the same year, it always fails in different conditions. Sometimes it will fail in high capacity, low capacity. Sometimes you fail working in summer, sometimes in the winter. And what we see is that every failure, what I call is a newborn, is a new thing. We never saw it before. Yeah, of course, the pump failed, but what caused it to fail? How it looked in the data. Did it fail right away or it developed by time? Every time is different. The indications are always unique. And this is a huge, huge challenge, and this is which is very unique for the process industry. Now, let's see what machine learning can do. So machine learning can do one way. One way is to use supervised machine learning. Supervised machine learning sells the dream. Be honest. They're telling you, give me all your failures. Give me every time that the pump failed, give me. All the time that the compressor fails, give me those failures. I will learn those failures. And I will tell you before the next one will arrive. When we look at the level, perfect. But let's go into the details and see if it can actually work. In order to create a prediction such as you need to create a statistical model. This is well known. Everybody understands. Everybody agree with me on that. In order to create this statistical model, you need to have at least, and this is at least 30 identical failures. So if you want to find why this pump failed in X situation, you need to have at least 30 identical situations when this pump failed to create the model. Now, you know it better than me that it's not that you don't have 30, 20, 10, you don't have 3 identical failures on the same equipment. So I'm very sorry to say that even though dream can come true, supervised machine learning for the process industry will just not work. Not because supervised is not good, it's amazing. But for the process industry, you don't have enough failures to create a statistical model. The other way around is to use unsupervised. Unsupervised says the opposite. I don't care about failures because they rarely happen. I want to understand what is the normal state of the plant. When I know what is normal, and then when things are not normal, when we have deviations, anomalies, I'll give you an alarm, an indication, something is not right. How it works. So the issue here or how it actually works is that, think about it, when you try to go into analyzing all the data. So if we're looking about the data that we are analyzing here with unsupervised machine learning, is that we're looking about 13 months of historical data, minute by minute. So we're talking about more than 500,000 lines. And what the machine learning is trying to do is to understand what is normal from this 500,000 lines and thousands of tags. And it do it very well. But the problem is with unsupervised machine learning, or the challenge here, is that because you have so much data, it just creates too much noise. You get endless amount of false alarms. I'll give you the quickest example. Think about a unit in a plant, an area of, let's say, I don't know, 3,000 tags. One unit, one process line. If you get one anomaly, only one every 5 or 10 minutes on around 3,000 tags, yeah? In a day, you get 150 to 300 anomalies. And it's too much noise. Nobody can really handle it. And it's a big issue because you get too much false alarms. Nobody have the time to look at it. And even if they do look at it, only 2% are meaningful alarms. So it's not that it creates too much noise, it's just wasting too much time. How can we be focused? Now, what we noticed is that what some other companies are doing, saying, don't look at the entire plant. Even though it's mandatory because you don't know where the next issue is going to come from. But let's look just on a compressor, a pump, and a heat exchanger. Because those are more critical for me. And I'm putting aside that you're already monitoring those type of critical equipment with different softwares years before. At the end, I don't know how long it will take you to implement, but even if you be successful on those 5, 10 equipments, at the end, you want to cover everything. And this is completely unscalable from time-wise. And also once you scale and you cover everything, you go back to the noise. And what we understood is that even though machine learning is amazing, and it really is, it's incredible, it's got limitation, especially for the process industry. And what we noticed is that if you're adding some kind of context to the machine, like giving him some kind of hints, it can be very, very accurate. And this is what we do. We're basically providing an additional layer of information from the plant in a very fast and easy way, which I will show in a minute, to the machine learning. And therefore, it's much, 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 much more accurate. And this is why one way to address the challenges is to look at predictive maintenance and on those unforeseen and unexpected events, because this is the ones that eventually appears, because this is the main area of unsupervised machine learning, to find those surprises before you're having the failure, before you are getting the unexpected shutdown, before the availability goes down, way before it gets to the control system. We're not replacing control. And if you want to look a bit into the details, you see that this is the value of non-repeating problems. So in 2 months, this is a report from one of our customers, we saved in between 142 to 4 million. Now, why the gap is so big? Because at the end, nobody knows what could have happened if SamGuard was not there to alert in time. And therefore, sometimes changing a sensor would cost you $1,000, but if you don't know that you have a bad reading or the sensor is frozen, and then the pump or the compressor can fail, and you're losing a day and a half of production, it can cost you millions. And the nice part here is how we do it. How we are able to get to these numbers from those unforeseen events, and putting all in a very nice package of let's do it fast with very pinpointed. So what we notice, in order to add this context of how the plant is going to the machine learning with a very fast phase of implementation, which takes us around 2 weeks, which we cover the entire plant, up to 10,000 historian tags. It's quite a big unit or a small, let's say, plant. Depends on how you structure the plant. What we do, we take in the PNIDs together with the engineers on site, and in less than 10 business days, we're converting them into our studio. Very simple and easy process, which I won't get into the details here, but in very high level, we're building a structure of the plant where we have each equipment, what we are measuring under each equipment, and then afterwards, we are connecting each equipment measurements to another one which are related to the same process. So we know to combine, let's say, the pump and the valve to the valve to the pump to the valve to the reactor. So we understand the context, we understand the process. We know which one is influencing when and how and each. And therefore, we're adding another level of information to the machine learning. In machine learning eyes, it looks like this. Basically, we are converting the PNIDs and the processes into the plant, to the studio, which then reflects to a graph. What we do now, we are basically reflecting the machine learning models on the graph. So what's the advantage here? The advantage is if we see an anomaly here, here, I know it's nothing. I know it's just noise. But if I see 20, 50, 100 anomalies in a specific area which are growing, and I know all the relationships and the connection between them, I know it because this is what we've done in the one-time implementation. I know exactly which one is influencing the other. Then I can tell you very accurately where to look. And this is what really makes us special. Try to summarize everything very quickly before we go to some use cases. And now we have very nice polls that we have for you guys to answer if you may. I'll be more than happy for it. In general, this is what every unsupervised machine learning company will do. And I won't go into supervised because supervised will basically will not really work. So every unsupervised company in the world will do this. Everybody will take historical data. They will analyze the data with the unsupervised machine learning, create baseline models based on the historical data. Then online data will come in. The outcome, and this is critical to understand, the outcome of every unsupervised machine learning in the world, including SoundGuard's, by the way, ours, is false alarms, and a lot of false alarms. But what we do, we're basically adding another level of information. We understand not only the relationship between them, we know the causality. And therefore, we are super pinpointed, accurate, and we're able to provide an average of only 5 alerts a day for the entire site. This is a great example to actually prove how it actually works. You see there's one of the measurements here are completely unstable. It's very picky. And if you look at it in machine perspective, each and every one of them is a potential anomaly. But as you see, our system did not generate any alarm here, not even here. Why? Because maybe it probably happened before. It's not really unique. Well, when did we alert it was here. Why we alerted here? First of all, it probably never happened. Again, those unforeseen and unexpected issues. And second of all, what you can see right away is that the relationship change. And this is critical. This is how you need to know when something is happening, because when you have one jumpy, it doesn't mean you have a problem. But when two things are changing and they have never behaved like that before, well, hold it. Something is going on. Yes, do we have any questions, or we can move to some use cases?
I have one question. Can you hear me, Dror?
Yes, I can.
That is from Jules Oudmans, and he's asking, is our approach based on...
Yes? Wait, I lost you when you said our approach is based on?
Our approach is based on SBM, similarity-based modeling. I think it's a kind of a definition, technical definition.
We need to go to ask our R&D team to that level of technical question. Okay. I'm sorry, I just don't have the answer for this question.
I write down your name, Mr. Oudmans, and we will come back to you. Thanks for asking.
I will try to answer something similar. Maybe we will not give you the right answer, but then Jos will come back with the full answer. The way that we are doing our clustering, basically we are modeling, creating what we call environment per equipment. And then we found a way to really connect not only between the equipments, but also between the measurements within the equipment. That's what really that's what's unique about us and about our patent. So I think this is similar in the area of what you've asked. Yours will give you a much more accurate answer once we go after the webinar. Anything else, Jos? Jos, any more questions?
No, I don't think so. There were some questions in the chat. I guess I answered them.
Cool.
So we can move on. Yeah.
Perfect. So let's look at a few use cases. So this is a furnace in a chemical plant. Now, when we started, we talked about unforeseen, unexpected issues. It can come from, it starts from very low numbers. So this is a bad sensor. Okay, there's a bad reading here. I think it dropped to 0.00007. Everybody understands it's a bad sensor. But you all know that you cannot have all the sensors monitored in the control room. You can't put limits of everything. And here, as you can see, this is the power of the technology. When both tags went down, the relationship changed. When both measurements went down, there was no alert, there was no meaning, because even though it's not, the furnace is not working, but it's not a problem. But when this one dropped, it causes something was strange. Something is happening. It never happened before. Now here they were lucky that we find it on time because they just changed the sensor. It cost them $1,000 to change the sensor. But if they will keep trying to drying the material in this chemical plant, and they have no idea what is the real number or what's the real temperature of the material that comes out of the furnace, and if it's starting to get too wet, eventually you'll get a blockage. Now, when this furnace is let's say, chunk, there's no more, it cannot work, they're losing production. This is the most important furnace within the site. So we gave ahead of time before actually preventing a blockage and putting aside the loss of product. It's the production until you clean it, and if you need to change something, the value here is obviously. This is a human mistake that the operator went to the pump. There was missing some fuel. Some oil, so he just put too much fuel. Don't ask me why. Maybe it was just the end of the can. He wanted to fill it up. He didn't want to bring the can back to the closet of the cans. I have no idea why. Because he puts too much oil, the pump could not rotate as it should be, and it got heated very fast. And if we were not there to alert, the pump will probably and completely fail, and the motor will be completely destroyed. So again, those unexpected and unforeseen events, here there was no damage done. They reduced the amount of oil. You see it over here within the green measurement, and now everything's fine. We didn't save them $1. $1 would not save them, but the potential value of what could have been happened here is tens, if not hundreds of thousands of dollars. This is a great vibration example of a pump station that we alerted. Think about there's a plant, there's some kind of pools that they are pulling up material from the pool. It's like tens of kilometers from the plant, so it's very far away. And in the middle, they have pump stations. And here what we noticed, and we were the only software that were able to identify that something is happening within the vibrations. And we told them, go take a look. And for them, it's an issue because they need to create an order for someone to take a car and go check the pumps over there. And they don't really know why, because some got alerted. It was just when we started. When they arrived, they saw that the concrete, the infrastructure of where the pumps are sitting, is starting to get cracks. So what they did, they just fill it up with some cement, and then everything's fine. No more issues. But if we were not there, the cracks will become bigger and bigger and bigger. This specific pump will probably fail, and then maybe the other 4 pumps that are over there will also get damaged. So again, the cost here was $1,000 or $2,000 for them to fix the issue. But the potential loss of what could have happened if this pump, or maybe the pump station, would be completely destroyed, it's within the millions. So try to summarize and leave some more time for questions as I would like to. So I think what makes us very unique is we cover the entire plant. I heard that some others say that they can. We actually do. I think 80% of our projects are covering the entire plant from A to Z. And we don't care about the type of equipment. We cover everything. One of our customers is saying that we are helping him identify the darkest corners of the plant because, the compressor and the heat exchanger or the pump, which is important, you monitor anyway. And we will monitor them as well, give another layer of defense. But what happens to the other parts that you don't have time, the eyes, the ears, to look at every day, and they're also important. We are detecting those unexpected issues from parts failures, process deviations, blockages, overflows, and more. We have a network of experts that can really help you achieve that, because sometimes culture change are a much difficult issue than software and technology. Implementation is really fast. So in 2 weeks, you're up and running, cover the entire plant. It's that fast. I dare you to test us. And at the end, we will save you maintenance costs, and we'll be here to increase your availability.